Hello, and welcome virtually to Brookhaven National Laboratory. I'm Bob Gordon, and I manage the U.S. Department of Energy's office here at BNL. Before you begin exploring this amazing place, let me tell you about the Department of Energy, Brookhaven's owner. The Department of Energy's Office of Science provides most of the lab's $700 million annual budget. We've hired Brookhaven Science Associates, a partnership between Stony Brook University and Battelle Memorial Institute, to run our laboratory, and especially the conduct of world-class science. You probably didn't know that the Office of Science is a world-leading supporter of research in the fundamental sciences. Battelle and Stony Brook are both leaders in science, education, and research. Together, we strive to realize the DOE mission to ensure security and prosperity through transformative science and technology solutions. And you're part of it. Welcome to BNL's Summer Sundays and enjoy the visit.
Hello, and welcome to this Summer Sunday, brought to you by Brookhaven National Lab. Today we'll be exploring two exciting colliders, RHIC, the Relativistic Heavy Ion Collider, and the EIC, the upcoming Electron-Ion Collider. My name's Daniel Marks, and I'm a research associate working on the accelerated design of the EIC. Over the next hour or so, we'll have a chance to see some of the inner workings of RHIC and discuss with an expert panel of scientists and engineers who work on RHIC and the EIC. You'll have the opportunity to ask us questions, and we'll do our best to answer them in the time available. Please just post them in the chat feature on whichever platform you're watching at any time during this broadcast. We've also got a few challenges lined up for you and encourage you to post your answers to those in the chat. So RHIC is a 2.4-mile circular collider located at Brookhaven National Lab on Long Island. It's a unique facility that has been gathering invaluable data from ion collisions over the past 2 decades. It has a few years left of operation, after which we're going to transform it into a brand new collider. That will be called the Electron-Ion Collider, or EIC, which will probe the inner structure of the nucleus using electrons. So as you can see, there's lots of interesting and exciting physics to discuss today. So let's start by introducing my colleagues who are joining me on this broadcast. So first up is Jean Van Buren, and those of you who watched last year's broadcast might recognize this man. So Jean, please introduce yourself.
Thanks, Daniel. So as Daniel said, my name is Jean Van Buren, and I'm a scientist on one of the detectors at the RHIC facility. And to tell you a little bit of something about myself, I'll start with something that happened in the 1630s, which is that a Dutch man came over to the United States. Wasn't the United States at the time, of course, and had a child on the boat on the way over and another child when he got over here. And one of those children became the 8th president of the United States, Martin Van Buren. And 13 generations, the other child's descendants ended up with me. So that's who I am, part of where I'm from, many immigrants to this country.
Very interesting. Okay, so let's, I didn't know that at all. So let's move on to Travis. So Travis, I know you work at RHIC, so tell us a bit about yourself.
My name is Travis Schrei. I am the RHIC machine specialist. It's my job to get the machine set up and to keep it running optimally when we change energy or we change ions in the machine. Outside of work, I like to mountain bike. I coach and play volleyball, and I like to build stuff. I have a machine shop set up in my garage, so I'm currently fabricating an old motorcycle back to life.
Wow, that's also very interesting. So next up is Kayla.
Hi, everyone. I'm Kayla Hernandez. I am a new electrical engineer in the Collider Accelerator department working on RHIC. Before this, I was a technician in the same department. And something interesting about me is I didn't actually start off liking engineering. I wanted to be an environmental scientist. When I was in high school, I worked in a biology lab at Stony Brook, and I weighed and measured the sizes of different leaves, and I was paid in cereal.
Thanks, Kayla. Let's move on to Mathieu.
Hello, everyone. I'm Mathieu Valette. I work on RHIC and the Electron-Ion Collider on topics related to machine protection to make sure the machine runs safely without any damage or radiation. And I would say a fun fact about me, except the fact I am French, but you can maybe tell from my accent, is that I grew up in Japan, and people don't usually expect that.
Thanks, Mathieu. I would have never guessed that you were French, but good to know. And last but by no means least is Elka, who I know plays a very important role in the EIC. Maybe tell us a bit about your role there and also about yourself.
Yeah, so my name is Elke Aschenauer. I work both for RHIC and the Electron-Ion Collider. I came here actually to Brookhaven to make the science case for the Electron-Ion Collider, which we have done successfully. That's why we can now start building it. And a fun fact for me is I have by now lived in 8 different countries all around the world for my work, for most of them.
That's a lot of different countries.
Yes.
I won't ask you to list them now. But,
no.
We can discuss
Thank you
that
very
later.
much, Daniel.
Okay, so thanks everyone. So over this broadcast, over the next hour or so, one of the things we'll be doing is having a quick tour of RHIC through a few different videos. So we're going to now turn to our first video, and Will Jackson is going to give us a quick overview of RHIC.
Hi, my name is Will. We're here at the Relativistic Heavy Ion Collider, or RHIC for short. It's an amazing machine that allows scientists to see what atoms are made up of. We know that atoms make up all the matter around us, but there's still much to learn about what makes up atoms. RHIC takes atoms without their electrons, now called ions, and smashes them into each other to find out what's inside. Scientists study these ion collisions to learn what the early universe was like and how atoms make up all the matter we see in the universe today. RHIC collides 2 beams of ions head-on while they're traveling at close to the speed of light. The particles actually start their travel far from the collider and travel through a couple of smaller accelerators. They get faster and faster until they are injected into RHIC, where the beams of ions go in opposite directions around the larger ring. At top speed, the ions can circulate in RHIC for up to 24 hours. For most experiments, RHIC uses ions of gold, but it can also collide other types of ions too. It can also use single polarized protons, which is important for understanding proton spin, a property used in MRI scans, but something that scientists don't fully understand yet. Results from RHIC experiments show that the early universe was like super hot supermatter. This matter is called the quark-gluon plasma, and it's about 250,000 times hotter than the center of the sun.
Okay, so we're back now. We're going to turn to our first question for you, and it's a true-false question. So please play along. All you need to do is type true or false in the chat. T and F are fine if you can't be bothered to type it. So please give it a shot. Here's the question. To get the ion beams ready to be collided with each other, we accelerate them to 99.995% of the speed of light. So, right, please write your true, false in the chat. I'll read it one more time. To get the ion beams ready to be collided with each other, we accelerate them to 99.995% of the speed of light. So that's the question, and maybe Kayla, you can take that one.
It's true. Getting and keeping ion beams moving so fast requires RF cavities. But first things first, what is RF? I'm going to share my slides with you so you can see what I mean. So RF is wiggling electric fields. Electric fields can push on charged particles like the ions in the beam at RHIC. We use special electric fields that wiggle back and forth like the picture you see here. They wiggle thousands or millions of times each second, just like the Wi-Fi signals that you use to connect to the internet or the radio waves your car picks up. That's why it's called radio frequency, or RF for short. RF cavities are specially shaped structures. Physicists and engineers make them with a very specific geometry so that they can resonate at a particular frequency. When you think about resonance, imagine hitting a tuning fork. Different size tuning forks resonate to different frequencies. They make a higher or lower pitch sound. One of the simplest shapes of the cavity is sort of like a soda can, except of course with the beam pipe going through it. When you drive the cavity, when you apply RF energy to it at just the right frequency, you can get really high RF fields on the inside. So why do we care about resonance? Like we said earlier, we want the beam to go fast, nearly light speed. So we need to accelerate the beam. We like to say that we have to kick the beam. When it passes through a cavity, you want to apply RF energy just as it crosses. Have you ever pushed someone on a swing? When you stand behind them, you have to push at just the right moment to get them to go higher. Linear accelerators like BNL's, LINAC, and Tandem are sort of like that. The beam gets kicked as it goes through each sequential cavity. If we lined up everything correctly, the RF waves in the cavity allow the beam to surf along, to speed up. But kicking the beam isn't the only thing that the RF does. RF cavity controllers can be used to change its shape, merge bunches of beam together, and line up the different circular accelerators like gears to move beam from one machine to another. Once the beam is circulating in RHIC, and it's just the right size and shape, it needs to be lined up with the beam moving in the opposite direction for collisions in an interaction region.
Okay, thanks, Kayla. So you mentioned the word bunches, and I think maybe we should come back to this. So in fact, our beam is not a continuous stream of particles, what we have in RHIC. We divide it then up into bunches. Is that right?
Absolutely. Bunches are kind of football shaped. They can be like up to 1 meter long, but they're very, very thin. They're very, very thin. They're very densely packed.
Yeah, and I think I read we have 111 in RHIC. So that's quite a lot of bunches over the ring. And that's important as well from an RF perspective, that it would be quite difficult to accelerate if we were a continuous stream, no?
Absolutely. Absolutely.
Also in the RF, these structures, are they at room temperature, or are they at a specific temperature?
Some of them. So a couple of the different RF cavities are copper. So we have these things called 9 megahertz, which is just a special frequency, big cavity in RHIC. And those are made of copper, and they're at they're normal conducting. But other cavities, like for different experiments, maybe those have to be superconducting, and they can be cooled down to as low as 2 Kelvin. So it gets pretty cold.
Yeah, and we'll come back to these cold temperatures when we talk about magnets. So let's move on now to our second video. And this is also from Will, who will now talk about magnets, in fact. So let's see that.
Special magnets called superconducting magnets steer the ions traveling around the ring. Let's go take a look at one. Here we have one of the RHIC magnets. There are 1,740 of these throughout RHIC. Ions travel through the beam pipe at the center of these superconducting magnets, which have to be kept very, very cold. These are chilled by 25 tons of helium to reach negative 452 degrees Fahrenheit. That's almost as cold as anything can get, around 4.5 Kelvin. Inside this magnet, you see a cross-section of the beam pipe where the ions travel. The beam pipe is kept under vacuum, so that way there's no other way particles or gases can interfere with the particles that the scientists want to see collide. It's also surrounded by coils of superconducting wire that can conduct lots of electricity without losing energy, and that allows the magnets to carry large current and create a very strong magnetic field to steer the ions around the RHIC ring. The superconducting wires are surrounded by insulation, and there's also space for the helium to get piped in and out to keep everything very, very cold.
Okay, so here we're back. We're going to ask you a question again. Again, it's a true-false question based on what you've just heard. So the magnets at RHIC are called superconstructing magnets, is the question. I'll repeat it one more time. Please place your true-false in the chat. So the magnets at RHIC are called superconstructing magnets. And I'm going to ask Travis to answer that for us.
Our magnets are called superconducting magnets, not constructing. But I'm going to get back to that in a second. Why do we need magnets in the first place? We haven't actually talked about that. So as Kayla said, when we want to accelerate a particle, we put it through an RF cavity. So you have two choices. You can make a train of many cavities in a row, hundreds maybe, to get to a high enough energy. Or you can cheat and put a couple in a row and then somehow make the beam go around and go through it many, many times. What we choose to do in RHIC is we do the cheat part. RF cavities are very expensive. They're one of the most complex parts of the machine. So we have a couple cavities, and then we need to bend the beam into a big circle and send it over and over again through those cavities. In RHIC, the beam goes around about 75,000 times a second. That's a lot of opportunities for kicks to go faster and faster. So how do we do the circle thing? Well, that's where magnets come in. So I have here a bar magnet. This is the kind of thing you stick on your refrigerator. Everybody's used to this. And a simple paper clip. You get it near it, and there's a force. It pulls the clip in. The same thing actually happens to charged particles. If you orient your magnet correctly, and you have a charged particle going into the screen, as it goes by, it feels a force towards the magnet. So it goes by and gets a deflection. If maybe it deflects it 10 degrees, it would be possible to put 36 of these magnets in a circle, and you could constrain the beam into going around. Now, one of the problems is the faster the beam goes, the more it takes to bend. So at low energy, this same magnet might deflect at 10 degrees, but as it gets higher and higher in energy, it will only deflect at 1 degree. So now you need 360 magnets to do the same job. That clearly is not going to work. So at that point, that's when we need to go to electromagnets. So I have a very sad little setup here that's barely visible. So there's nothing special about this. Anybody can do this at home. This is a nail. I wrapped a piece of wire around it 20 times and a D-cell battery. So like I said, this isn't a setup. Nothing happened if I hold the paper clip to the nail, it just falls. But if I run electricity through this wire, it now becomes magnetized. I take it away, it falls. Do it one more time, take it up and take it down. Now, why does that work? Electricity and magnetism are actually two aspects of the same force. You can use electricity to create a magnetic field, or if you move a magnetic field around, you can actually create electricity. That's how the alternator in your car works. So what we do in RHIC is that we make our magnets oriented in such a way that we can contain the field into a very small area and make a very high field. And the faster the beam goes, the more current we run through the magnet. The more current you run through it, the stronger the magnet gets. But one thing I do want to say, if you do this setup at home, it's a very easy setup to do. If you're a kid, have your parents help you. No matter who does it, don't touch your finger to the part where the wire touches the battery. Because you're running a decent amount of current through there, it gets hot very quickly. That, in fact, is why it becomes important to have a superconducting magnet. So a regular conducting magnet, we put all this current into these magnets, thousands of amps, that create a very strong field, but ultimately all that energy is turned into heat. We can't recover it. The nice thing about superconducting magnets is they don't really generate heat. You can put a lot of current through a superconducting magnet, and once it's in there, it just loops through it because there's no what's called resistance to it. So it doesn't take much power to keep this thing running. Now, the downside is, I think in that video, Will said we have a very large refrigerator. There's no free lunch. If you're not paying for the energy one way, you're paying for it another way in the form of a refrigerator. So we have to keep the magnets at 4 degrees Kelvin. The Kelvin scale starts at absolute 0. Nothing can get colder than absolute 0. So it's a very cold assembly. We use thousands of gallons of liquid helium in order to keep this stuff at that temperature.
Okay, thanks, Travis. Now, you've talked about.
Can I actually just ask Travis a question really quickly? Because I know that these magnets draw a lot of power. Is that right? You were saying?
In the injectors, yes, they draw a tremendous amount of power.
And I think that I've seen some issues that we have on the power grids from the fact that you guys draw so much power.
Right. So the booster accelerator is the smallest one. It's about 200 meters. And it ramps up and down many times a second. The rep rate is about 200 milliseconds, so 5 times a second. It goes up and down. We draw all this current into the magnets, and then we have a lot of the current. It doesn't go away instantly. We shove a lot of that reactive power back into the grid. So it's constantly pulling and pushing on it. And if you live close enough to the lab, sometimes if you have a dimmer on an old CFL light, you can see the light wiggle a little bit, and that's because of the booster.
Wow. So you described these magnets that bend the beam round the ring. So those are called dipoles. Those aren't the only types of magnets we have in the ring, though, are they, Travis?
Right. So a dipole magnet is responsible to bend. We have quadrupoles, which I don't have a good, well, actually I could do it. So if you have 2 regular bar magnets and there's a north and a south, and you orient them correctly, it would actually be like this. You wind up getting field lines that will do something interesting for focusing. So like Kayla said, we accelerate things in bunches. Those bunches have about 1 billion particles in them. They very much want to get away from each other. It's all like charges repel. When we create these bunches, they aren't all going in the same direction. They have some angular variance, so they want to spread out. So it's important to be able to focus these things. So a quadrupole magnet acts like a lens. In optics, though, a lens will focus in all planes. Unfortunately, a quadrupole magnet only focuses in one plane and it defocuses in the other. So it's not really intuitive why that helps. Why does it help that one plane gets blown up? Well, if you take that same magnet and then roll it 90 degrees, you blow up in one plane. And when you go down a little further, you then focus it. So what you wind up doing is creating a stable envelope for all these particles to stay in. And that's how we keep them happy in the machine. So we're able to keep some of these stores for up to 30 hours. I think 32 hours, I think, is our record.
Yeah, and in fact, that technique you described, I think, was pioneered at Brookhaven in the middle of last century.
Right. The alternating gradient synchrotron was the first time that somebody tried what's called strong focusing.
Mm-hmm.
It enabled the beam to be stored a lot longer than anything prior to it.
And we still use it, no?
Yes, the alternating gradient synchrotron is actually the machine. So the beam comes into the booster, gets accelerated up to a certain energy, goes into the AGS, goes even higher in energy, about 99% of the speed of light, and then we hand it off to RHIC, which is, like you said, 99.995 the speed of light.
Yeah, so it's quite a complicated machine altogether to get our ions right up to be ready for collisions. So I want to remind our audience now that you can ask us questions. We're monitoring them and we will do our best to answer them. So please do post them in the chat and we will come to them. So talking of collisions, let's take a look now at where the collisions happen. So we're going to turn back to Will, who's going to show us.
To get collisions, RHIC is 2 accelerators in one. Each one is made up of those long superconducting magnets strung end to end like beads on a necklace. At various places around the ring, physicists steer both beams into a single beam pipe so the particle beams can collide. Huge detectors surround this interaction area and record signals that tell what kind of particles come out of the ion collisions. The signals that the detectors pick up provide physicists with information about the conditions created in the particle collisions.
Here we're at RHIC's STAR experiment.
Behind me is the shield blocks, and behind the shield blocks is a 1,200-ton magnet detector for STAR's experiments. It's about as large as a 3-story house. STAR specializes in tracking the thousands of particles produced by each ion collision in RHIC. It looks for signatures of that quark-gluon plasma. RHIC detectors have picked up signals that tell us not only is super hot quark-gluon plasma created during the ion collisions, but that matter also has no viscosity or resistance to flow. It is technically a perfect liquid. Scientists have also observed that gluons play an important role in proton spin. Another large detector, Phoenix, is now being transformed into a new detector named S-Phoenix. It will be able to study some of the most intriguing particles that are created in RHIC collisions. Nuclear theorists continually refine their calculations to help make sense of the data and compare the experimental results with physicists' expectations.
Okay, so that was, hopefully you found that interesting. Now, as usual, we'll turn back to a true-false question for you, the audience, to please post your answers then in the chat too. And this question is, RHIC experiments showed that the quark-gluon plasma was a perfect gas. Once again, RHIC experiments showed that the quark-gluon plasma was a perfect gas. And I'm going to ask now Jean to answer that, please.
All right, so that's a question for seeing whether you're paying attention to the video and paying attention to what Will said in the video. And the answer to that is false. And it's just on the detail of the last point there, that it's not a perfect gas that we found, it's a perfect liquid. And what I'd like to focus on is the fact that before we built RHIC and operated it and made the collisions happen and studied what happened in the collisions, people had predictions for what we would see out of collisions like this. And it was predictions like that that drove us to do the experiments, to do the experiment of colliding nuclei in this way at these energies. And we had some understanding of the matter that we were colliding before we did all of this. And the predictions said, okay, well, we know that when we get to really high energies, the force between these particles actually drops off and gets smaller, diminishes. And the interaction between the particles becomes weaker. And in a very good sense, that's essentially what a gas is like and what differentiates a gas in some ways from a liquid. In a gas, the particles are essentially free of each other generally and move around quite freely, while in a liquid, the particles kind of stick to each other and stay together. That's different from a solid where they stick together and hold their positions, but in a liquid, they still move around. So the essence of the predictions was that we were going to see at these really high energies that these subatomic particles that are down inside nuclei were going to get so much energy that they were going to just get to that region where we expected very little interaction, sort of a weak substance, a weak matter that we produce. And that would be like a gas. And that's why you do the experiment, because when we did the experiment, we found out that that's not what we see. In fact, the particles do interact strongly with each other still. They do separate from the structures that they were in inside nuclei. But as Will mentioned in the video, it's sort of like a soup. They stay together in one larger mass of stuff that we call a quark-gluon plasma. And that was very educational for us to do the experiment, to find out what happens to this matter under these conditions. And our predictions aren't always exactly right. They guide us in what to do, but sometimes you just have to do the experiment and see. So sometimes you have to wrap more wires around that nail in Travis's electromagnet, or put more current through the wire and just see what happens. And for us, it's a bit more complicated than that, but it's still the same idea that by experimenting, we learn more about the truth of the way the universe works.
Yes, so that's an important result which RHIC has given us. we have many questions coming through, so want to turn to the first one, which is from Jim on Facebook, and he asks, what does a particle collision look like with the naked eye? Is it a flash of light, an explosion, or is it so small you can't see it? So that's a very interesting question. Mathieu, do you want to start us off with that?
Yes. So the detectors we have at the RHIC facility have spectrometers and calorimeters that allow us to identify a lot of the various particles that can be emitted during a collision, like one in one of the displays that Will has shown. Our eyes, though, can only perceive visible light, which is a very narrow band of the electromagnetic spectrum. So if you were to look at a collision of particles with the naked eye, you might see a flash of light if photons in the visible spectrum are emitted in your direction, which is very unlikely. And one of the main things that will happen to you if you see a collision of particles with the naked eye is that some of these high energy particles will be running through you, which you should definitely avoid because this is basically radiation. And this is why at RHIC, we have a very complicated access control system to prevent people being in the tunnel at the moment where collisions happen.
Okay.
Perhaps a related question I get asked sometimes is, what do the collisions sound like instead of what do they look like? And similarly, it's not something that you're going to experience. There for a couple reasons. One is that for sound to happen, you have to have some kind of medium that the sound propagates in. So sound is a compression wave through a medium like air, or you can hear sounds underwater too. And when the collision happens, there just isn't enough material for the impact and the compression and the waves of energy that come out of that to propagate out into something that would then eventually propagate through the air into your ear. So you would never hear that. So that's one reason. Second is that the amount of energy in these collisions, it's a lot of energy for two nuclei. And that's why we say we can reach really high temperatures, because for those two nuclei, that's a lot of energy, and essentially you can create a high temperature within that amount of stuff. But if you add up what the sum of that energy is on our human scale, or even on the scales of sounds that we hear in our everyday lives, it's tiny. The comparison people like to say is that it's like two mosquitoes colliding, and you probably wouldn't hear that.
So Jean, we talked about looking at them, we talked about listening to them. In fact, what we actually do, of course, is use detectors. And we have a question from Ankit on Facebook. And the question is, what kind of detectors are used at RHIC?
Yeah, Matthew mentioned a little bit about them. And it's quite a variety of different kinds of detectors. But the main idea of a detector to see subatomic particles is that you need the material of the detector to essentially feel some kind of effect of a particle going through it. Just like your eye is a subatomic particle detector that detects photons of light, when those photons of light then reach the back of your eye and produce an effect on the back of the eye. Just like your ear is a detector, you get an effect with a sound compression wave affecting your eardrum, essentially, right? And then moving the drum. So you have detection in your own body, and your eye, I think, is a very good example of a subatomic particle detector. And so while the detectors that we use to see the particles isn't exactly the same as a human eye, the idea is really the same, and that is that you have some kind of response to a particle going through it. So the way I kind of like to think of it is that you have atoms in some kind of material, could be in a gas or a solid or a liquid. And as a high energy particle comes out of the collision and goes through that detector material, the atoms in that detector material feel that particle coming through. They may feel it because they get exactly struck by that particle going through, in which case they may deposit all of their energy into some form of movement or even creation of light inside that material. And then you look for that light. Or even if you don't have a head-on strike of a particle in the material, as the particle goes through the material, the atoms in that material might sense that particle coming by through, for example, the electromagnetic force if it's a charged particle. So you get a little, ooh, something just went by. And that can be enough to trigger a response in the material. It can, for example, excite electrons in that material so that they release light as well, and then you look for that light. So there's a whole variety of different kinds of detectors that we've made to see different parts of essentially the spectrum of particles that come out of the collision. Spectrum in terms of what those particles are, and spectrum in terms of what the energy of those particles are. So we can look for low energy particles, high energy particles, particles of one variety or particles of another variety. So rather than list the variety of detectors, I'll stop short and say that there are a large variety of detectors, and we try to utilize anything and everything that can reasonably work well for us.
Okay, thanks, Gene. We have actually, you talked about energy. We have a specific question from Chang on Facebook about how we detect energy and momentum. Perhaps you want to tell us a bit about specifically that measurement.
Well, I think a good example of an energy measurement is something, Matthew mentioned a calorimeter, and the word calorimeter is one that hopefully you can break down and understand a little bit. I think people are generally familiar with the idea of a calorie, which is a measure of the energy, and meter. So you're measuring energy. So a calorimeter measures energy. And the way it does that is generally something along the lines of what I just said, where you have a particle comes through into the material and you make a very, very dense material, so that the chances of it actually hitting and depositing all of its energy into that material are high. And then you try to look for the response to that impact in the material, and the amount of response tells you the energy. So that's a good example of measuring energy. And then coming back to momentum comes back to what Travis was talking about with magnets, because magnets tend to bend a moving electrically charged particle. But as he pointed out, something that's moving faster is more difficult to bend. So instead of changing the magnet, we keep the magnet the same, but you see that a higher momentum particle will bend less than a slowly moving particle. And so you can try to track how particles move and see if they bend a lot in the magnetic field or bend just a little bit in the magnetic field, and that's a good way to measure momentum.
I see. So I should remind, because we have a question also about which particles we're colliding. I guess we're colliding anything from protons in RHIC to heavy ions. And typically gold is used, often gold is used at least, isn't it?
Yeah, and my guess is one of the collider guys here can tell you more about the different things that they've accelerated, but we've asked for a lot of different things and they've provided a lot.
Sure. Travis, do you want to add anything?
Yeah, so this is one of the few facilities in the world that can do polarized protons. So if you take a hydrogen atom, the smallest atom, and pull its electron off, what you're left with is a single proton. So we have accelerated protons. We're actually going to be doing that next run. We're going to be doing a polarized proton run. And then on up from there, we've done copper, we've done aluminum. Gold is our workhorse. That's generally what we do when we run. Deuterons, which is like heavy water, and then you strip that off. The heaviest thing we've done is uranium. That was a pretty fantastic run, but yeah, we've done a very large number. And in fact, RHIC is so flexible that he can actually do protons on gold. So like Kayla said, things are generally shaped like a football, but you can probe things in different ways by having smaller things hit bigger things. So protons against gold is a very different effect. And instead of having two buses collide, it's like having a bullet hit a bus, and you learn different things from those different shapes.
Okay, so we've looked now at nuclear physics experiments at RHIC. We talked quite a bit about those, but those aren't the only ways that these ion beams are a benefit to science. And in a complex of accelerators, some particles we also use for other types of research. So let's now go to our last stop, we will, at the building with RHIC's main control room.
So here we are in the building with the main control room. Behind me is a mural of one of the smaller accelerators, the AGS, Alternating Gradient Synchrotron. Operators such as myself make sure that all of these smaller accelerators and systems are running correctly. And from here, physicists can also steer particles to facilities that explore the effects of space radiation, so we can help protect future astronauts. And to make important isotopes for diagnosing and treating diseases like cancer. All of these programs will continue to move forward as RHIC begins to finish up its experimental program. In the near future, a major collaborative effort will transform some of RHIC's components into a brand new nuclear physics research facility, an Electron-Ion Collider, or as we like to call it, the EIC. It will be two intersecting accelerators, one with a beam of electrons, the other with a beam of protons or heavy ions. It will be able to produce three-dimensional snapshots of the internal structure of the protons and ions. Like RHIC, the EIC will be funded by the federal government through the Department of Energy's Office of Science and will draw on expertise from throughout the DOE National Laboratory Complex and at universities and research institutions around the world. EIC partners will include the Thomas Jefferson National Accelerator Facility, Jefferson Lab, and Newport News, Virginia, as well as nearby Stony Brook University and other international participants.
Okay, so let's give you now one more question. And again, true or false question, please type your answer in the chat. So here's the statement. The EIC will be a brand new nuclear physics research facility and already involves scientists from all over the world. Once again, the EIC will be a brand new nuclear physics research facility and already involves scientists from all over the world. Is it true or is it false? Please type your answers. And I'm going to ask Elke to tell us about that.
Yes, so that is absolutely true. The EIC is a new research facility which we are lucky to be building at Brookhaven National Lab, and actually with our partner from with Jefferson Lab, which is another lab actually sitting in Virginia in the US. And we have collaborators already from everywhere in the world. You find a country and somebody is working on the EIC. So now you probably ask yourself what the EIC is doing. And for this, I share quickly actually a picture, which hopefully you can see well. So what you see here, actually, what we want to do is the EIC, you can think about a microscope, which will really unravel the mysteries of visible light, visible matter. And what that means is, you basically have a human body, and a human body is made out of atoms. And then these atoms, in this core of them, they are made out of nuclei, and nuclei are made out of protons, the other particles which we are actually accelerating. And then if you have this really high resolution microscope, what you can see is that these protons have actually substructure, which are then these quarks and gluons, which are actually really have the name according to what they do. They glue the quarks inside the proton. And so if you have this microscope, the Electron-Ion Collider, you can discover really all this universe, which is there beyond what you can see, but makes up everything which we see around. So what we are actually trying to answer is how this visible matter, which we see, the trees, us, our tables, chairs, and so on, are actually made out of the smallest building blocks, these quarks and these gluons inside the proton. And that is one of the things. And also how they get mass, which is actually also very interesting because all of these particles have mass and we don't know how they get mass. So if we could understand this better, maybe we would have a better way actually to kind of also lose weight if we would like to. So that is one of the things. But another thing, Travis mentioned already that the RHIC is the only machine which can accelerate polarized protons. And that is actually something which we want to use as well in the EIC. One of the things we want to understand is, where is the spin of a particle coming from? And you can think about, if you're a child, you probably had one of these twists which are kind of rotating and spinning. And exactly that is what these quarks are doing inside the proton as well, and the proton. And we use this actually in our daily life all the time. If we go to a doctor and get an MRI, then we actually use the spin of the proton We put ourselves in a big magnet, we kind of flip the spins all in one direction, and then we get a picture. But what we don't understand is how really the proton gets its spins off the quarks and the gluons. And it is actually a mystery, which is there since 30 years, where people thought, it's trivial to explain. Until now, we haven't really. And that is something which the EIC will also do, to understand where the spin comes from. And then there is still a lot of other things which the EIC will do if we are getting it built in something like 2030. That is when the EIC is supposed to become actually online and we can do experiments.
So what's the big difference from RHIC with the EIC, Elke?
So the big difference is that we are not colliding like gold and gold. No, we take gold nuclei or protons, and then we have electrons. And these electrons are actually very nice because they are very small. So if you collide gold and gold, it is like you take a hammer and smash the other gold. Here, you take something very fine, it emits a photon, so basically like a visible light. And then you can kind of use this, you shine this on, and then you can reveal really kind of very precisely the substructures. And that is very different to the RHIC, where you really kind of maybe take more like a hammer to kind of see the substructures. So that is the big advantage of the EICs, that we really can use like a microscope with an infinite resolution to kind of see what is happening inside nuclei and the protons.
Okay, thanks, Elke. Now, the EIC, of course, we're going to use the same tunnel as RHIC. And I have a question now for the audience, again, true or false. The EIC will be built entirely from RHIC's components. Is that true or false? Once again, the EIC, the Electron-Ion Collider, will be built entirely from RHIC's components. Give you a few more seconds to post your answers. And then I'm going to turn to Mathieu and ask him to answer.
Thank you, Daniel. So the EIC will be reusing the existing RHIC facility, but as we need to collide electrons with the ions, we will need to build the whole accelerator chain in order to have electrons colliding with the ions. So I will share one slide here with you now, where I show a schematic view of the EIC overlaid on top of this aerial photograph of the RHIC facility. Here you can see what already exists. In green, the injection chain for RHIC, and the yellow and dark blue rings are the two rings that are used in RHIC right now, and all the rest would be new. So the facility to accelerate electron with the linear electron accelerator that would inject its beam into the electron injector that would ramp the energy of the electrons in order to inject it into the light blue ring, which will be the electron storage ring. That way, we can store the electron beam and collide it at the location of the two detectors that will be made especially for the EIC program. Now, there will also be a need to operate with low energy ions, and there will be an infrastructure installed in order to cool these ions, because as Travis said, the ions in a particle beam, they repel each other. And in order to keep the beam focused, we will get some help from an electron cooler, where we use the negative charge of the electrons to cool down the positively charged ion beams. And this whole electron cooler facility will also be constructed. Now, if you think about it, the RHIC tunnel, as you have seen in the video, is not very large. And you can see here a cross-section of the tunnel where the two existing RHIC rings are already there. And we will be adding this electron injector, here you can see on the right, and the electron storage ring to it. So the tunnel will get quite crowded. And then there are a lot more upgrades that we will be performing on the RHIC accelerator itself in order to make it ready for the EIC run.
Yeah, and in fact, all of these, in a way, these whole accelerators and colliders are a tool in the end for us to use and to look at the collisions and the data which comes out. But in itself, the building this machine is by no means trivial, and it's something which comes with many challenges and many new aspects of physics, which we have to investigate. So I'm working, for instance, on this light blue ring, the electron storage ring, and I can say there are many challenges that we need to overcome and many interesting aspects of physics involved in building the machine itself. So whether we're working on the accelerator, on detectors, or looking at the data, there are all sorts of challenges involved in a project like the EIC or like RHIC, and all sorts of different aspects of physics. So, which makes it very exciting. But let's turn to some more of our viewer questions. And one of them is on Facebook. We have, can you simulate particle collisions using supercomputers and data from experiments at RHIC? So that's an interesting question of, so both about computing, maybe Elke, do you want to tell us a bit about that?
Yeah, so absolutely. So this is actually what we are doing. We are simulating, we have models of actually the interaction. So we simulate the physics. And then we have models of the detector, how the particles which we are creating in the collisions are actually interacting with the detectors. And we put both together, and then actually we kind of simulate what is happening. And we use computing facilities all around the world, kind of like also at CERN with the distributed computing. We put the data there, we analyze them, we kind of put the simulations. And then actually we compare what we see in the collisions with what we have modeled. And if we put different physics in the models, then we can actually understand what we see. So yes, we use this absolutely every day if you're a physicist, to understand what you are seeing, to understand how the particles interact with the detector, because that tells you more what particle it was and what happened really in the collision. So yes, we do this. That's our daily bread and butter. Yes.
I'd like to add to that there's a lot of computational power needed for a lot of this work, just both for the simulation side that was the focus of the question, and for the analysis of the data. And so we need some top world-class type computing facilities to do all of this work. And we push on computing technologies. So some of the stuff we do is sort of at the front of leading technologies for things like artificial intelligence. We try to make use of big data, cloud type things, and supercomputing facilities is among the different things that we use. So part of what we do, like Elke said.
Yeah, and that will continue to be a challenge moving forward to the EIC, no, Elke?
Yes, absolutely. So actually for the EIC, because Jean just mentioned artificial intelligence, there we want to actually integrate artificial intelligence right the moment where we take the data out of the detector, so that we kind of know already very quickly what it is. Is it a real event we are interested in, or was it something which we are not interested in, which we very often call background. So we want to separate signal from backgrounds, and there we use also artificial intelligence, and we will put basically GPUs like you use for gaming really on our readout electronics to get the data out. So, and then continue on. So again, a lot of simulation, a lot of computing and writing code to actually analyze the data. Yes.
Yeah, and there's another interesting question about detectors from Jim on Facebook, and he asks, are you aware of any limitations of your detector that would cause you to not notice important byproducts of a collision?
So I can actually answer this. That is part of it, what we do also with the simulations. So our detectors are actually not always 100% efficient. There might be a part which gets broken because maybe a readout, that is the part electronics gets broken and so on. And then we actually simulate this and can kind of understand this. We monitor, we have basically channels which we use to monitor very simple things which tell us this. And sometimes you might maybe not know. So you always know as much as you monitor and what you know about. And so it could be that something can escape once in a while. But we are really pushing forward that we make our detectors as efficient and well-performing as possible.
Yeah, and we, like Elke said, there are things we want to make sure we understand we don't know before we try to use the equipment that we use. Sometimes we do learn about our limitations through experience a little bit. Like I was bringing up when Travis earlier was talking about magnets and how the power that they use can actually impact our systems, or potentially the RF that Kayla was talking about could impact the science that we're trying to do. So sometimes some of it we can't learn about until we actually try.
Yeah, and Rick does certainly have many years of experience, which must help. Now, one question I always get asked when I tell people I'm working on accelerators or colliders is people always ask me about the LHC. That's the Large Hadron Collider on the border between France and Switzerland. And that's a 27-kilometer collider, or 16.6 miles, I think. So it's the biggest machine in the world. And people are obviously interested in this. And in fact, we have a question from YouTube. Can you use the LHC for electron-ion collisions? So that's an interesting question. Mathieu, can you tell us a bit about that?
Yeah, so it happens that I used to work on the LHC prior to coming to Brookhaven National Lab. The LHC in its current status cannot be used to accelerate electrons because of the polarity of the magnets. It would require a lot of changes to use the LHC to accelerate electrons. And there is also the fact that when you accelerate electrons, they emit a very strong synchrotron radiation. And the LHC right now would not be able to accelerate a significant quantity of electrons without having problems with this synchrotron radiation. But the thing is, you have to know that the LHC was actually built using the tunnel of the lepton electron. The LEP was the lepton electron
positron collider.
Yes, exactly. So the LHC was built using the tunnel of a previous machine, which was colliding electrons prior to the LHC's existence. So there was already an electron collider of this size. The one thing that was not done is using a facility the size of the LHC to collide ions with electrons, which is the brand new thing that we will be doing at the Electron-Ion Collider.
Yes, and one we should also mention, there are actually interesting design plans to build an electron, to add electrons to the LHC, so to collide electrons with hadrons, which are not at the stage of the Electron-Ion Collider at Brookhaven, but are nevertheless interesting plans, which may or may not come to fruition.
True,
so
I think it's fair to say that even if we do the LHEC, it will not as unique as the EIC because it has not polarization in the protons. And even to polarize the electrons will be very challenging. So the EIC is in that case a really very unique machine worldwide because it can basically do all the tricks which you need, whether it's polarization, ions, and so on, which you need to really understand visible matter. So it is very, very unique.
Yeah, and we should also mention from looking back in history, is the Electron-Ion Collider the first of its kind? I know you worked in Germany. Elke,
Yes.
maybe you can tell us a bit about
that. Is true, it is not. So there was the HERA collider at DESY in Hamburg in Germany. And actually it had higher energy, the electrons as the protons. But again, it had only the electrons polarized, not the protons. It couldn't collide ions. So it was the first one. It discovered a lot of really interesting things about the proton structure, but it couldn't really study all the things which we want to do with the EIC. And that's why we actually built on the EIC. It also has basically what we call a higher luminosity, which means that we can collide more particles per time unit and area unit than the HERA could. So it is really a very unique facility, what we are building here at Brookhaven.
Yeah, and there'll certainly be interesting results coming out of it. We should say, just in terms of the timescale of the EIC, we're currently working on the preliminary design, and this is something which we plan to work on over the next decade, the design and then the construction. So that should be, we have a very exciting time ahead and a very busy time ahead for the EIC. Let's take one more question from our viewer questions, and it's how hot does it get in the general vicinity of a particle collision? So we've already talked about about very cold things in our accelerator, but what about the heat in a collision? Gene?
So I think it's going to depend on how you define vicinity. So where you are. If you're actually in the matter that is colliding, right there at that point, all of that energy from those two incoming nuclei or protons, or eventually with the EIC, even with an electron, you're bringing all that energy into a very small space. With an electron, it's an even tinier space, so it's really, really difficult to discuss it as temperature in such a tiny little volume where that collision is. But in the collision volume where, for example, two nuclei collide, that is a lot of material coming in, a lot of matter coming in with a lot of energy. And as they come in, that's energy in the form of directed motion. And then as they collide, a lot of that energy becomes energy of random motion, which is what we refer to as heat. And so that is essentially temperature because it's heat. And so you could measure the temperature of that. And so in that vicinity right there, we're talking about trillions of degrees. But if you step away from that, as the particles expand and fly out of this collision zone, they're spreading that energy out quite rapidly. And over essentially, once they get to human type scales, that energy is so dissipated that the temperature from that is small on our scales. But so depends on how close you want to be.
Sure, but it's quite amazing how we have one machine, we have almost the coldest thing we can make, and then something which is incredibly hot, not so far away.
Yeah, and if you put your hand, in the beam of particles, that's a lot of energy going through. So that's not the kind of thing you want to consider.
Yeah, I don't think we should be doing that anytime soon. So yeah, as you can see, it's a very exciting time for us at Brookhaven National Lab, and also for the community all around the world who are closely involved in this research, both at RHIC and EIC. And certainly these advances which we make, both the advances in science and also technical capabilities, the engineering challenges which we use to build these kinds of research facilities, will continue to develop and improve our understanding of the fundamentals of matter and energy. So certainly a very exciting time ahead. And let's just turn to one last question for all of us, for the panelists. Then it's a more personal question. So what would you say is the best part of doing the work that you do? So that's a question. Maybe let's start with Kayla.
Thanks, Daniel. I don't think that there is one path to Brookhaven National Lab. And I think I can speak for most of us when I say if you talk to anyone on site, no one, graduated high school or started their freshman year in undergrad thinking that they'd end up where they are right now. Most people's lives are more interesting than that. But if you're interested in becoming an electrical engineer at a place like Brookhaven, you need to get a bachelor's degree in engineering science. And then you'd want to pursue a master's degree. And just to put in a plug for the great work that our support staff does, OEP, the Office of Educational Programs, has plenty of internships for high school students, for undergrad students, and there are great opportunities for postdocs at the lab as well. So at any point in your educational path, if you're interested in being a part of the work that we do at the lab, not even just at the Collider, you can go on the educational tab on the Brookhaven National Lab website, and you can find out about the internship opportunities that we have here. Personally, I was recruited. One of my electrical professors, he thought that I was good at circuit design, and so he passed my name along, and I was interviewed and hired as a technician. And then I worked as a technician while I was finishing up my bachelor's degree and then I applied to be an electrical engineer. But everyone's path is different, and no path is completely linear. So don't get too caught up in your plans. Allow yourself space to grow and to be fulfilled in whatever you do.
Yeah, thanks, Kayla. And there's also an interesting video I know of you, of part of the Science Thursday series, where I know you talk about more about that. So if people are interested, I encourage you to have a look on the Brookhaven's video channel to find out more about that. So Kayla, what would you say, what do you love most about your work?
I think you've already said it, the work. I'm never bored, ever, not even once. Things are always interesting and always exciting. At the Collider Accelerator Complex, we have so many different machines. I get to work on linear accelerators, circular accelerators, and of course on RHIC. So I get to have my hands in the very tiny electronics that are controlling very minute details like LEDs and inputs and outputs. And I also, when I'm very lucky, I get to work on like machine to machine interactions, moving beam from one machine into another machine, things like that. So I think working at a lab always keeps me at the edge of who I am, and I'm very grateful for that.
Yeah, and I think we'd all agree with you there. Travis, same question to you. What do you love the most about your job?
Jean mentioned it earlier. We plan, we model stuff. We like to think we know how things are going to work, but we're constantly surprised. So the point of RHIC is to provide beam to the experiment so they can do their experiment, but the machine itself is kind of like an experiment. A lot of the times it doesn't behave the way we expect it to, and that's actually some of the most interesting stuff. Trying to figure out why the machine is behaving the way it is when we do a new configuration, and it happens now more and more. We used to start up the year, we would set up the machine at the beginning of the run, which was generally October, November, and it would take like a month to get the machine set up. And then we would run continuously for 5 to 6 months, and then we'd shut down. We would do one thing. This last run, I think we ran 5 or 6 different energies and a couple different ions and even mixed ions. And every time you go to switch the machine around, something gets you that you're not expecting. And then doing all the troubleshooting to figure out why it's working the way it is it's pretty cool.
Yeah, it must be very exciting being in the control room. Jean, do you have any new things to say? What do you?
Yeah, well, first, it's always annoying that the Collider people have to figure things out every time. But well, to add something,
I think there's a button. There's like, why don't you just push the collide button?
Right. To add something new, in addition to, I completely agree with things both Kayla and Travis said, is to say that I really appreciate the chance that I get to meet people from all different walks of life on all different parts of the earth. And, you know, you learn something from everyone. And, you know, not everybody is, you know, the kind of compatible person for you to spend all your time with, but they bring a lot of different experiences to share. And a place like Brookhaven National Lab is where people come from all over, and you get to experience that.
Absolutely. And I'm in calls almost every day with people of all nationalities, from all sorts of different labs. So it's really also for me, I very much enjoy that aspect. Mathieu, anything you really enjoy about your work, which is different, you want to add?
So I totally agree with what Travis said. Like the collider itself is already like an experiment in itself, and it's sometimes difficult to figure out what's wrong, what's not working. Just to add on to that, I think one of the great things I like about what I'm doing here is like the opportunity to be working on an existing machine, the RHIC that is working, and the operations of it, and also the design of a new machine, because you can get inspired by what is maybe you would like to improve on the existing machine to make this new machine in the future that you hope will be perfect, but eventually in the end, when people are running it, they will turn into problems, just like when we are operating RHIC. And yeah, I like how it's different every day. Some days I'm doing some programming, some days I'm doing some complicated physics simulations, some days it's just simple things like planning and conflict resolution, which is not always simple. But yeah, it's different every day. And yeah, I think this is one of the great parts of working on the accelerator.
Yeah, certainly we're never bored. Elke, anything to add?
Yeah, so for me, is the most fascinating one is that the people all around the world can unify peacefully around a science question and really try to address it together without any kind of conflicts. And it is diverse. It can be, doesn't matter who the people are. You kind of come together and kind of resolve this. And of course, with the EIC, for me, the most fascinating thing is to see really from the first idea you have about the science to really see how you can get such a project and really build and launched and take data from, in 10 years from now. So that is something which is absolutely amazing to see.
Yeah, I couldn't agree with you more. And also a personal note from me, we sometimes, we do our day jobs and we kind of go into a routine. And sometimes it's useful to step out and to think, this is really amazing what we are doing. We are at the cutting edge of science and technology. We are doing something. We are answering the questions which humanity has had forever. In the end, what are we made of? What's the universe made of? This is the same questions Greek philosophers were asking. Now we have the tools, we can finally do that. And to be part of a huge effort to answer such questions while addressing such interesting physics challenges along the way is really a great privilege, I think. So I think that brings us towards the end of our time here together. That was very enjoyable, I think, for all of us here, and hopefully to our viewers. I hope you enjoyed yourselves and also learned a lot about the kind of research we're doing at Brookhaven National Lab. Hope you will follow us as we continue on this journey towards the end of RHIC and through the EIC. So next week, there's a continuation of this Summer Sunday series. The third Summer Sundays will be all about the Center for Functional Nanomaterials. So that should be very interesting. It will be a different team of scientists from that facility at Brookhaven National Lab. So do join at the same time next Sunday if you can. So, but from all of us, please stay safe. Please stay in touch with the lab, stay in contact, and stay curious. Keep asking questions. And that concludes today's Summer Sunday. Thank you. Goodbye.
Bye-bye.